So I was saying the problem that I will use to motivate a little bit why we are interested on these topics is one of the so-called measurement problems. I know there is a senior measurement problem in quantum mechanics. This is what I call the junior measurement problem. So it's something very much operational, and it has to do with the fact that we are now, as you probably know, building larger and larger devices. We hope that we are going to be able to run more and more complex algorithms, but we still need to extract information from these large quantum states that we prepare on the devices. And typically what we want to do is to measure an expectation value of some sorts on our state. And okay, I will not be fully general for the moment. Let me say a few things that are mostly relevant for the near-term scenario, then I will also generalize a bit afterwards. But in the near term, the way you usually want to do this measurement is by projecting in some basis. And if you knew the exact eigenbasis of your observable, what you would really like to do is to measure directly in these eigenbasis. Unfortunately, we don't know typically how to prepare or to rotate the basis into the eigenbasis of our target observable, also because sometimes the answer that we want to get from our algorithm is, for example, one of the eigenstates, like typically the group state. And even if we knew, sometimes the basis rotation is so complex that we are going to waste all of our coherence time of our qubits just to do this basis rotation. Instead, typically in the near term, what we do is that we, for example, decompose this observable into a series of Pauli strings with some coefficients. This is a basis for our space of observables, so it's fine. And then we measure these Pauli strings individually or in small groups, like commuting groups, for example. Unfortunately, this method is not optimal. And there are different reasons why this is suboptimal. One, for example, is that even if we were able to prepare the exact eigenstate of our observable, as soon as the observable is made by a set of non-commuting Paulis, we don't have zero variance in our expectation value, even if we prepare the exact eigenstate. The error is going to be instead a weighted sum of errors on the individual Pauli strings, for example. And we have this very nasty, like Monte Carlo-like scaling in the number of shots that we need to take on our machine. So we have to take the number of shot scales with the inverse of the square of the error that we're going to make. This typically gives us some resource requirements for typical applications like quantum chemistry and so on that are incredibly large. So we need to find a better way of doing these measurements, especially if we want to make near-term quantum computing applications useful or practical. As I was saying, in principle, we know already a much better method to do this, which is resorting to something like of the form of a quantum phase estimation algorithm. This reduces dramatically the number of shots that we need to take, and in general gives us what can be called an Heisenberg-like scaling in number of shots. So we get a scaling that is inverse with epsilon instead of with epsilon squared. The price that we typically have to pay is that we need to implement something that looks like phase estimation. So a much deeper circuit compared to what we can do right now. There have been some proposals on how to do something intermediate between the two. You pay a bit of price in terms of circuit depth, and you get a bit of a better scaling in the number of shots. But really what we most of the times are left to, if we want to really do something today on these devices, is having a very short circuit budget to rotate our basis and to prepare the measurement, and then pay the price in this Monte Carlo-like sampling of the expectation value. And of course, if you go in the literature, there have been a lot of different proposals on how to do this with different methods. There is, as I said, the idea of doing some local basis rotations and group the Paulis into commuting sets. You can be very sophisticated in doing this. There are some advanced application-oriented basis rotations that you can do in polynomial depth, even linear, and you can significantly improve the number of commuting groups that you can get. You can use neural network state tomography, which is a very powerful tool for this game, and of course the well-known family of classical shadow techniques. The way we wanted to approach this is with POVMs, so informationally complete measurements, because we thought, okay, this is the most general class of quantum measurements that we can do on a quantum device. Let's see if this helps in any ways. I think I don't have to go through the technical introduction about POVMs for this audience, but just to give a minimal introduction, a POVM is a set of operators M, MK, which we call also POVM effects. They are positive operators, they sum to the identity, and they respect the Born rule. So the probability of getting outcome K from our measurement is given by the trace of the state times the POVM effect. And then particularly interesting class of POVMs, like POVMs are a general class, they contain all the projective measurements that we know of. There is a particular subset of all POVMs, which is particularly interesting, is called informationally complete POVMs, because essentially you are not bounded by the size of your space in choosing how many POVM effects you have. And if you have enough, you can essentially span the space of all emission operators. This means that with an informationally complete POVM, you can set up your experiment in such a way that you don't need to change anything. You just collect shots, and in principle, you're able to do full state tomography. How do we use them to do expectation value estimation? Well, as I said, if you have an informationally complete POVM, you can decompose your observable in terms of, you can span this observable in terms of the effects. You get something like this, and if you do the expectation value, you get a product of coefficients times probabilities, and this is something you can solve with a Monte Carlo integral directly. So you're going to have still the same scaling that you had before, like with a number of shots, but now you have, as I will explain in a moment, a bit of more control over the variance that shows up here at the top. So this is
yeah. Very short question. These POVMs are still local. Like,
okay, you can, in principle, you can have non-local POVMs. So you can do them on n qubits. Of course, this is highly impractical. So for the rest of the talk, I will only consider implicitly assuming that we do product POVMs. So informationally complete POVMs on single qubit, and these are still informationally complete on the total state. It's just that they capture only correlations. In principle, you can do more. So I put numbers here because this is going to be a bit of an outline of the rest of the presentation. For the first, so the key points about these informationally complete measurements is that once you collect them, you can reuse this informationally complete data to estimate the observable you were interested in, but also something else. This is the whole principle that is also common with classical shadows. With every, let's say, informationally complete randomized measurement toolbox, there is this nice sentence that you find in this review that says that the principle is that you measure first, whatever, and then you ask your questions later. You have a particular observable in mind, fine. If you forgot about something, you can still go back to your data and measure those properties afterwards. We had a few questions about like using POVMs in this setup. One is, what is the optimal measurement given, for example, a state or one or more observables? What can we do? There are many different informationally complete POVMs that we can take. What's the best one? And also, what are the best strategies to post-process the informationally complete data, so to construct estimators for different observables, for example? And what's the connection exactly with classical shadows? And of course, since we also want to do experiments, how do we actually implement these POVMs in practice? There are a few ways, and I will talk about like standard Naimark dilation strategies, either with ancilla qubits or with like higher levels systems. But of course, for some of these POVMs, you can also simulate with randomized projective measurements. This is very easy to do experimentally. So we also asked ourselves the questions whether this particular part of the protocol is sufficient or optimal in certain sense. Okay, this I think I can go very quickly on. You know that the set of POVMs is convex, so you can take any two POVMs and combine them into another POVM by essentially randomizing the choice of the POVM itself. In this way, you can construct essentially linear combinations of POVMs. And the set of POVMs, like the consequence of this is that the set of POVMs is convex, and there are few extremal points on this set. All the projective measurements are extremal, are on the boundary, but not all points on the boundary are projective measurements. So there exist certain POVMs that you cannot, informationally complete POVMs that you cannot implement just by randomizing the choice of a particular basis. This means that the set that we are able to implement most easily in experiments is not complete. It's not the full set of POVMs. So it's a legitimate question to ask what we can do inside of this part of the set, while we might be able to implement a few of these, but certainly not.
If you ask a question.
Yeah.
Your strict attention to POVMs where every operator is a multiple. Is that complete? Does that cover all the extreme ones? Because every PSD operator can be written as a sum of projectors.
Yes, I think in that case you can.
Okay.
Yeah, but the problem is that whenever you do PM simulable ones, you'll always have an effect, and it's opposite in a sense. For example, for a single qubit, you'll only have something like this. So you can choose the measurement basis, for example, and your effects will look like something like that on your log sphere. But in this way, you are never going to be able to do like a tetrahedron, which is the symmetrically informationally complete. As I said, this is for example a very typical example of a randomized POVM. It's called the Pauli-6 measurement. It is also what people commonly call a classical shadow measurement. It's actually a local classical shadow measurement when you randomize the choice of the Pauli on every qubit. You can do it with equal probabilities, or you can also change the probabilities by which you choose the different Paulis, and you're going to change a little bit the POVM that you are doing, and do even more general stuff. Okay, so far so good about the general theory about POVMs. Now let's go a little bit more into how we actually use this to the sampling and estimation of observable. So the typical experimental setup is something like this. So you have an input state, you do some algorithm, and then you at the end implement this informationally complete. And now for simplicity, let's assume we only have one qubit, so we have 4 possible outcomes. This is the minimal informationally complete POVM for a single qubit. And what happens is I run once my experiment, I get one of the 4 possible outcomes, let's say 0. I collect it, and then I go into my observable. I say, okay, what's the coefficient corresponding to outcome 0? That's omega 0. I put my bin, I populate my bin here. And the red line is going to tell me what's the current average, the current expectation value that I measured. Okay, I measure another one, I get 3, I populate bin 3, I get 1, I populate bin 1, and in the meantime, you see that the red line is moving, and okay, I complete the population, the collection of my IC data, and this is the expectation value that I collect from my observable. Okay, now suppose I have another observable now, like B, with other different coefficients. Now I don't need to redo the experiment again. I just take this set of IC data and I populate the bins of this other observer. And okay, there are some cases where this is working quite good. In this case, you immediately see that there is already something that's not proper. Like you see that the distribution of these bins is very wide, is very broad. And the consequence of this is that you're going to have to make a big error in estimating the set of IC data. This is because essentially what we call the single shot variance, which is what appears here at the top of this fraction, is going to be either large or small depending on essentially this term here. This one is just the square of the expectation value, and it doesn't depend on the POVM. But this term depends on which POVM you choose. So our first question was, okay, can we adjust the POVM to minimize this single shot?
Just to be very clear, omega k is kind of dependent on the choice of POVM.
Omega k is dependent on the choice of the POVM because it also depends on the observable, of course, and pk as well. Like the probabilities will also depend on the choice of the POVM and on the state. In all of this, we are assuming that we have a fixed state that we want to target, and we only care about how do we choose the best POVM or a good enough POVM for this. Okay, so the point is that now we want to focus on this term at the numerator here, and we want to try to adjust it with the choice of the POVM to minimize it. This is not going to do anything about the scaling, the Monte Carlo scaling, of course. It's just changing the prefactoring, but it can make a big difference in practice. So as I said, we focus on this term, like the single shot variance, and as I said, this term we can actually disregard because this does not depend on the choice of the POVM, but this term in front here, it does. And okay, the first idea that we had was, okay, POVMs are informationally complete. So if I take a collection of shots, I can estimate with these shots which kind of error I am going to make if I used another POVM, because I can always take a second set of effects, express them as linear combinators of my current effects, and then rewrite the expectation value of the square of the expectation value according to this. I can reuse the probabilities of the outcomes, but I need to do this conversion between one POVM and the other. This doesn't work because in general, you have exponentially many, let's say, effects that you need to convert. So you can, in principle, use a POVM to estimate the error that you would make with another POVM, but this is exponentially costly. So this is not going to work. What we did, in fact, is to do a gradient descent in the POVM space, leveraging the product structure. So if you use local POVMs on the different qubits, then you can parameterize those, and the parameters will only enter one of these, like one of the indices at a time. So it's easy to compute the gradient with respect to a certain parameter because it only affects a local part of your POVM. So in this case, you can. And so you can essentially do a gradient descent in the space of the POVM where your cost function is basically this first step. The result is something like this, like it's a loop of this kind where you have an IC POVM, you implement it in a parametrized way, you estimate while you collect the shots, you do small batches, you estimate the carrier variance, and then you adjust your POVM and you collect another batch and you go on like this. And you can also at the end, you reuse all the shots that you use to do a final global estimate that is going to be better and better the more you proceed. You have to do it in a weighted way because these estimators are all coming from the same distribution in the sense that they have the same mean, but they don't have the same variance. So you need to do a weighted sum of the estimators weighted by the variances. And of course, you want to spend just a few shots at the beginning to estimate, to adjust the POVM, and then most of the shots at the end when you know a good enough POVM to do your estimation. And what you will see is a curve like this. So this is a comparison, for example, for measuring the energy of a chemical molecule, comparing what you get with standard Pauli and Pauli grouping techniques compared with the POVMs. What typically happens is at the very beginning, you pay a bit of a price by using these informationally complete measurements because these are also very unsharp measurements. So you have a big prefactor in general if you don't optimize it. And then the more you proceed with the shots, you see that these lines are all straight lines with the coefficient -1/2. This is the Monte Carlo type of scaling. In this case, it seems that you can beat this Monte Carlo scaling, but this is fake. This is just because you're changing the prefactor a bit. And then after a while, you will basically continue with the -1/2 slope because you cannot optimize the prefactor indefinitely. The important thing is that sometimes, I mean, we need only to get to, for example, for chemical applications, we only need to get to this dashed line. This is what we call the chemical precision. So sometimes it's enough to just stop at some point. Okay, this was sort of promising. Of course, this essentially matches what you can do with, for example, classical. And after this, we started to think, okay, can we do this in practice on our devices? Like, can we really implement these informationally complete POVMs on our hardware? And there are a few textbook ways of implementing informationally complete measurements. They all connect to this idea that you can do this with projective measurements on a larger Hilbert space. So you expand your space, for example, with an ancilla qubit, and then you perform a unitary transformation on this extended space. You do a projective measurement on the extended space, and then you post-process the result, and you get your informationally complete measurement. If you do it with this tensor product strategy, you need an ancilla qubit for every qubit of your register, of your main register. And this is a bit, I mean, not easy to find, for example, on our current hardware connectivity. So you don't have from the very beginning an ancilla for every qubit that you may use for your algorithm. So at the end, just at the end, but at some point you need to like double the size of your processor. And this might be feasible or not, depending on a number of factors. We have a 100 qubit device. If we want to use all of them for For our algorithm, we don't have any more qubits to do this ancillary thing. The other one is a direct sum approach, where you extend the space in height. This is the ladder part of the talk. You know that many of the quantum systems that we use to do computation are actually multi-level ones. We just ignore the other levels, but they are there. For example, in the Transmon qubits, we have a few other excited states that we can access by engineering the pulses on our device. And we came up with a scheme by which you can very easily find a template of pulses by which you can access the 4 levels of the Transmon and implement any arbitrary 4 outcome 1 qubit POVM.
Yeah. So do you have any examples of implementing this on a 100-qubit device?
No, not yet. This one doesn't really work because of the connectivity problem. This one doesn't really work. I mean, we implemented it, we tested it on a very small example, but it doesn't really work because these qubits are really not made to use the higher levels. Like, our engineers make all the efforts possible to isolate actually the 0 and 1 levels from everything else, because they don't want any population to leak there. Yeah. And here now we are asking them to do the exact opposite, and they are going to be mad at us if we really ask. So this is a working design principle. Maybe it's better suited for Rapp-Dion's architectures or things like this, but it doesn't really work for superconducting qubits for practical reasons, like the noise in the higher levels is very high, readout is not easy. So we're left with the good old randomized protocol. So this is what really think is practical to do right now. So you just flip a coin every time, you decide which projective measurement you want to do, and that's going to give you an informationally complete POVM. Only one of the PMC block ones. And the question is, how well can we do with those? Can we, because we didn't do any assumption in our other experiments, so can we really match what we see with general dilation POVMs with these PM simulable ones? Well, that's a question. And before answering this question, I want to go a little bit deeper into the way you decompose things, because I will show you that there are other degrees of freedom that I didn't really mention up to now, which are possibly useful to improve the performances of these POVMs. So as I said, the variance can be adjusted by choosing the POVM, but it can also depend on how you form this decomposition of your observables in terms of the POVM effects. Okay, as I said, informationally complete POVMs are a class of POVMs where they span the whole Hermitian operator space. And if the number of POVM effects is exactly the square of the dimension of the system that you're measuring, this is a minimally complete. And this decomposition is unique. There's nothing you can do. It's basically a basis. This is what typically happens when you do 4 outcome POVMs, like the general class that we studied now. Is that if the number of possible outcomes is larger than this is still informationally complete, so you can do this decomposition, but the decomposition is not unique because this is an overcomplete set. So for a fixed state, for a fixed choice of the POVM, if the POVM is overcomplete, you still have the degree of freedom of choosing how to do the decomposition. And this will affect the variance of your estimators. So for a more theory perspective, the POVM is actually a frame, which is this generalization of a basis in a vector space where you have more, it's an overcomplete collection of vectors that spans the space. And there's this nice fact that for every frame in a vector space, there exists a dual frame for which, given any vector in the space, you can express this vector as a combination of the vectors of the frame, and the coefficients are going to be the scalar product between the vectors and the duals. This is the generalization of the usual expansion of a vector over a basis. So, as I said, IC POVMs can be thought as a measurement frame in the vector space of Hermitian operators. And in this case, what are the duals? What do they really represent? Well, if you try to apply the definition to a state, which is a member of the space of Hermitian operators, what you see is that you can express it as a linear combination of probabilities, so the scalar product between the state and the POVM effects, and duals. So the duals are basically statistical estimators for the state. and therefore they are basically classical shadows. So they are not quantum states themselves. They can be not positive in general. But if you take enough samples and you combine them, you are going to get a good estimate of this. So dual POVMs are basically classical shadows. And you can define this frame superoperator by which you can compute essentially the dual frames for a given POVM in this form. So you just define this operator, you take the inverse, and you apply it to the measurement measurement effects, and you get the duals. And when the POVM is minimally complete, this is unique, and it's given. It's called the canonical dual. If you're interested, there is this very nice paper where it was recently published in PRX Quantum, and you find a lot of information about dual frames and how they connect to the theory of classical shadows. Okay, if you apply this theory to the estimator, to estimate an operator, what you get is that essentially you can express this operator in this way, where now the coefficients are the trace of the operator itself with the dual frame, and the probabilities are, as before, the trace of rho, the state with the POVM effect. So it's completely symmetric in a way. You have state times POVM effects, and on the other hand, you have operator and POVM duals. So now the problem of finding an optimal measurement is actually can be phrased as an optimization problem on both the dual frame and the POVM itself. And again, in this paper, there are several nice results on how you choose the optimal dual frame given a POVM and a state. So if you apply those, for example, if you do it for a minimal IC POVM where you only have the choice of the canonical dual frame, then what you get is basically this one. So this is the most general formulation of the problem in terms of only the POVM. Okay, as I said, there are a few nice results, but as I will tell you in a moment, not all of them are really practical to be used in practice. So our task in our most recent work was to find a good way of, okay, if we want to just, let's say, parametrize this dual frame in a way that makes it valid, but still something that we can adjust at the post-processing level, how can we optimize it? How we can parametrize it in the first place, and how we can optimize it to improve the quality of estimators. There is a general theory on how you parametrize dual frames, which is textbook linear algebra stuff, which is nice, but it's also a bit costly. So what we devised instead is a formula like this. So we found out that if you write a generalized version of this frame superoperator where you put some coefficients here, and you define your dual frame in this way, so again as the inverse of this alpha frame superoperator, and you also multiply again by these alphas. If the alphas represent a probability distribution, so they sum up to 1 and they're all positive, this is always a valid dual frame for the POVM and defined by the effects MK. So you can get a non-exhaustive parametrization of the possible dual frames for the certain POVM by just choosing a probability distribution, essentially. And we can recover some known results with this parametrization. For example, if the alpha k is 1 for every k, you just get the canonical dual frame, and this is what typically classical shadows literature choose. If you instead take that alpha k is the probability of observing outcome k on the state, this is the probability distribution defined by the POVM on the state. This is the optimal dual frame given the state rho. This is a result that is proved in this paper. So if you knew the state, you could choose always the optimal dual frame in this way. And this is optimal for all the observables. I mean, you restrict this on the let's say, the support of the observable, and it's optimal for that particular observable. Instead, if you typically don't know the state beforehand, one thing you can do is that you can just take a guess based on an average for an unknown state. You just do this for the maximally mixed state, and you get an average optimal dual. Okay.
Sorry.
Yeah.
Can you go back one slide?
Yeah.
So optimal for an average unknown state, like how bad does it get if rho is kind of far away from the maximally mixed state?
I don't remember the bound, but can be very bad.
Okay.
I mean, this is the best you can do without assuming anything about the state. But if you, I mean, there is a continuum between not knowing anything and knowing everything, and this is what we're going to leverage in the next.
Yes, okay, but like in the classical shadows, it just chooses one. Like it does.
They choose one. This one.
Yeah. Does this beat like the?
I think it beats this one.
Okay. In many
I
cases,
will need to check, but I think it beats the average. Okay. As I said, we are going to use product POVMs because this is what we can manage classically. And if you think about how many variables you have, in general, you have exponentially many. So this probability distribution can have exponentially many terms, so can be very impractical. And also the dual frame, the duals of the POVM effects, even if the POVM is product, they can be non-product in general. In particular, if you use this optimal dual frame result from the paper, you get that, okay, it depends on the state, which is generally unknown, but also it leads to exponentially large duals, even if the POVM has a product structure. So it's optimal, but I mean, you have to think that duals are some things that we need to manipulate classically. So it's something that we need to store in the memory of our computer. We need to use just like classical shadows. We need to use them then to construct the estimators. They cannot be exponentially. So this optimality result is not practical, and we thought about how can we ensure that the duals are also efficient to process classically. Okay, a very easy choice is to choose the product structure in the probability distribution. Since we can parameterize the duals with a probability, if you enforce that the probability is a product over different qubits, then the duals will also be a tensor. This is very easy to see. So you can do this. You can enforce this locality by choosing a product probability distribution. If you instead choose a product of m local distributions, then you can enforce that the structure of the dual is a tensor product of up to m qubit of frames. So you can really bridge between fully non-local duals to clustered duals in a way, even if the POVM is by itself only a product. Yeah.
These m local distributions, they can overlap each other.
No, not didn't. So the proposal that we put up is something like this. So in general schemes, what you do is that, for example, you pick your over complete POVM like a classical shadow type of measurement. You collect the classical shadows and you compute the traces with the observable by using the canonical duals. What we proposed now in this most recent work is instead to also add at the post-processing step a choice of the best dual frame that you can practically use. And you can do a bit of an iterative optimization at this stage. And the nice thing is that you can do it, all of this can be done in post-processing. So once you fix the choice of your POVM, of course, you can try to optimize both of them simultaneously, and this will give you a bit of a cumbersome optimization problem. But even if you fix the POVM, you can still, for example, choose a different set of duals based on the observables that you want to measure. So IC data can be used to measure different observables, and for each one of those, you can pick a different dual. Or you can use the informationally complete data to estimate some properties of your state that will help you pick a good dual.
Is it similar as what you were saying in the beginning, that given a POVM, you can always kind of, if you have exponential classical power, you can always kind of transform it into another POVM?
Yes, but yes and no, because it's not symmetric in deep, because POVM's effects, you can change the POVM by changing that way, but you will still need to respect the positivity constraint of the duals. Here you don't.
Okay, yes.
So duals and POVM effects are basically the same thing, but not.
Yeah. But that might make it a little easier.
Yeah, exactly. So this one, I think it's easier. So we tried to apply this on some different classes of POVMs. We took, for example, locally biased classical shadows. This is the ones where you pick X, Y, or Z with different probabilities. This mutually unbiased basis, but you also add the unitary that makes you rotate the effects a little bit on the block sphere. you can also choose something that is it's non-orthogonal in the space. So you can choose X and then another thing that is not orthogonal to X as your basis. And then we wanted to compare this with dilation POVMs like this one, like tetrahedral POVM, which is of the kind that we think we cannot really implement. And our figure of merit was the single shot variance averaged over a set of random observables and states. So we picked a few random observables and states, and we evaluated the single shot variance, trying to minimize it by minimizing the POVM. What you see is something like this. So you see that this class performance, or this average single shot variance, goes down the more complex you have of a POVM you choose, from basic 6-outcome classical shadows to the 4-outcome dilation POVM. The nice thing that you can see is that if you choose the locals, the duals, you can improve the performance of the class quite significantly. So this is what the blue curves are essentially what you get with the canonical and the average optimal dual frame, which I think is an answer to you. I think the average optimal does better in general. Instead, if you do the optimized version local, you can gain a bit. Of course, if you can implement the optimal joint, which is what we could do in this case because we knew the state, and it was a single qubit experiment, so it's also small, this is where you gain the most in principle. And up to the point that you can essentially match the performances of a 4-outcome dilation POVM. So at least in this very small case, we could answer, not very formally, but we could answer numerically to our question of whether we can match the performances that you would get with the dilation POVM. So this shows you the improvement that you get just by doing local dual frame optimization, which is something you do all in post-processing. What we tried then is also to use the information a bit that we collect from the informationally complete samples to parametrize the POVM, the dual frame. So as I said, you can in principle do as we did in this previous image, you can optimize the POVM and the dual frame simultaneously. This is a bit of a convoluted optimization. One thing that you can instead do is, okay, I choose the POVM, I optimize the POVM, but then the dual frame I don't optimize. What I do is that I take the probabilities that I observe, the measurement probabilities of my dual effects, of my POVM effects, and I use this to parameterize this alpha probability distribution. So I use the outcome probabilities of my measurements to construct the best approximation to the dual frame that I want to use. Ideally, if you take infinite shots, then this is equivalent to state tomography, and this corresponds to taking the optimal joint dual frame. You can do this to avoid numerical instabilities. Usually you want to start, for example, from an equal distribution of probabilities, like start from the average optimal dual corresponding to the maximally mixed state. You just change this a little bit. And okay, if you do it without any assumption, you're also going to get back to the problem that the duals might be non-product. So to enforce that they have a product structure, you actually take marginal probabilities. So you enforce a product structure, the probability distribution. This you can do, and you can converge to, let's say, the optimal dual frame in a decent number of shots. You can also do a little bit better. So you can use this idea of having clustered probabilities, and you can, instead of marginalizing on single qubits, you marginalize on blocks of qubits. And which qubits go in which block, we decided based on the mutual information. So we took the mutual informations between pairs of qubits, and we prioritized grouping together qubits that have a high mutual information. Of course, there is the limit up to which you can group them depends on your computational power, the classical computational power. The more you can hopefully treat on the classical side, the larger groups you can have. But for example, here we tried with 1 local, 2 local, and 3 local. And what you can observe is that, okay, as you increase the number of qubits, as you might guess, the effect of optimizing the duals, I mean, it decreases. So the advantage that you get decreases. So you this is the variance reduction with respect to the choice of canonical duals. So the higher here means that you are closer to not doing anything, just choosing the canonical ones. And you see that if you just use this one local duals where you optimize for single qubits alone, you're going to get worse and worse. So at some point, you won't see basically any of them. On the other hand, if you were to use optimal duals, this gives us confidence that, I mean, at least in the limit where you could be using the optimal joint duals, you would be doing significantly better. Of course, this is not practical. In between, we have this. So if you can increase a little bit let's say the locality of your duals as you increase the number of qubits, you are going to do a little bit better than with respect to the canonical duals. Is this practical? Is this useful? They can be useful. Our guess is that they can be useful in settings where you only need to estimate k local observations, which is practically what we always want to do. So this is also the setting where, let's say, local classical shadows shine. Like this choosing a local random basis for Pauli's works very well if you have many k local Pauli strings. And this is the setting where we think also our dual frame optimization can be useful. And this is just an addition on top of all the good that classical shadows can bring. It's a for free improvement that you only get at the post-processing stage. We also think that, okay, maybe there are some relevant quantum states that have a limited correlation structure. So this is also something that can in principle leverage to build better dual frames. Okay, this is a bit of a summary of this. Maybe I forgot to mention, this was also a bit of an archaeology type of project because we realized that the theory of dual frames is very well known. I mean, it's not something that we invented. It's something where you find papers from the early 2000s about this. And we were inspired by this work that came up on PRX Quantum because they showed for the first time that there is a clear connection between these two things and something that the classical shadows literature somehow ignored up to now. So it's maybe not.
You're right, but also not.
You can tell me later which papers are using this, and I'm happy to acknowledge the idea. But I mean, with this work, we tried to really take an operational approach and see what exactly we can do by leveraging these additional degrees of freedom that are there, and it's a pity not to use them. There are a few open questions that we have. The main one that I think it's probably something we can also discuss, and I think this audience might be interested in telling me more about is, of course, a more formal performance and scaling analysis of this protocol and what's a comparison with more general classes of frames. I don't have any proof, any formal result on how good we can do, but I'm happy to dive deeper on this. Our operational question right now is: are there efficiently computable joint dual frames beyond what we devise now? What's an equivalent of what we call a Clifford-like dual frame? So something that is maybe highly non-local but still efficiently computable. I don't know if Clifford is a good way of calling this because I don't know, but in the sense of something that, I don't know, maybe a tensor network or something like this, where you can use efficiently computable but non-local dual frames. And also the question is how well we can then use all of the results by only approximating the knowledge of the state with a finite number. Just to leave you with a bit of outlook, where do we think we could apply these ideas? We have recently explored, for example, this idea of hybrid three tensor networks, where you have a quantum state that replaces a part of a classical tensor network. And here the challenge is really what to do at this interface between the classical and the quantum part. This is a nightmare usually. And we think that these classical shadows or duals are a very natural language to like connect classical and quantum like computational workflows. The other one, which I'm happy to acknowledge, is this recent proposal by the group of Sabrina Maniscalco and others at Algorithmic in Finland. They came up with this nice idea on how to do error mitigation based on tensor networks, and their starting point is exactly dual frames. So They have a noisy quantum circuit. They take duals of, so classical shadows of this. They convert it into a tensor network representation, and then they contract the inverse of the noise map, essentially, after this. And they can error mitigate, essentially in the spirit of like probabilistic error cancellation, but all done in post-processing. Really cool. Also, happy to acknowledge that there are a couple of results that are very similar to ours. We were, of course, discussing with them a lot about these topics. So again, from the group of Sabrina Maniscalco and also this other group, they did some very similar work on optimizing POVM duals for estimation of observables. So you can also check out these ones. And yeah, I'm happy to acknowledge the collaborators with which I did most of this work. This initial adaptive POVMs is something we did in direct collaboration with Algorithmic and the team of Sabrina. This is the paper where we did this dilation on QDITs. And this is the most recent work that we did on twist-wall frame optimization. And if you're interested, we have also a Qiskit toolbox on POVMs that is currently under construction, where we are hopefully going to put all of these tools for you to maybe explore and use. You find it at this link. It's, as I said, currently under construction, so you won't be able to use it now, but hopefully in the next couple of months. And with this,